Hello everybody. Today in this video we're gonna be doing types 2, way more types. There was an article about types. I don't know which number it is, but that was types 1. In that it talked about mostly about type def, I believe, if I remember correctly, right? In this we're gonna talk about way more types. Let's start that. We are used to character, int and float types, but now time to take that stuff to the next level and see what else we have out there in the types department. Signed and unsigned integers. So far you used int as a signed type, that is a value that can be either negative or positive. But C also has specific unsigned integer types that can only hold positive numbers. These types are prefaced by the keyword unsigned. Int a signed, signed int a, signed itself, signed a is signed shorthand for int or unsigned int, rare, unsigned int and unsigned C. Why? Why would you decide you only wanted to hold positive numbers? Answer: you can get larger numbers in an unsigned variable than you can in assigned ones. But why is that? You can think of integers being represented by a certain number of bits. What is this? I have what do you call a mouth canker sore, right, under my lips. I wonder how to not have canker sores. Bit is short for binary digit. Oh wait, I know what bit means. On my computer, an integer is represented by 64 bits. Now each permutation of bits that are either 1 or 0 represents a number. We can decide how to divvy up these numbers. Now with signed numbers we use roughly half the permutations to represent negative numbers and the other half to represent positive numbers. With unsigned we use all the permutations to represent positive numbers. On my computer with 64-bit, using 2's complements, representing signed, positive, negative and 0 integers on computers, and more generally fixed point binary values as the 1's complement, and sign manual systems. 2's complement uses the most significant print as the sign to indicate positive or negative numbers, and non-negative numbers are given their unsigned representation as 60100. However, in 2's complement, oh wait, that's 2's. However, 2's negative numbers are represented by taking the bit complement of their magnitude and then adding 1. Minus 6 is 1010. Right. So that's 2's complement. To represent unsigned numbers, I have the following limits on integer range. This much for signed integer and this much for unsigned integer. Notice that the largest positive unsigned integer is approximately twice as large as the largest positive integer. So you can get some flexibility there. Character types. Remember, character, the type you can use to hold a single character. I have a shocker for you, it's actually an integer. Deep down, character is just a small integer, namely an integer that uses just a single byte of space, limiting its range to. Here the C-spec gets just a little funky. It assures us that a character is a single byte, that is size of character is 1, but then in the C11 3.6 it goes out of its way to say a byte is composed of a contiguous sequence of bits, the number of which is implementation defined. Wait, what? Some of you might be used to the notion that a byte is 8 bits, right? I mean, that's what it is, right? And the answer is almost certainly. But what do you mean almost certainly? The industry term for a sequence of exactly indisputable 8 bits is an octet. Oh. But C is an old language, and machines back in the day had, shall we say, a more relaxed opinion over how many bits were in a byte. And through the years, C has retained this flexibility. But assuming your bytes in C are 8 bits, like they are for virtually all machines in the world that you will ever see, the range of a character is. So before I can tell you, it turns out that cars might be signed or unsigned depending on your compiler, unless you explicitly specify. In many cases, just having car is fine because you don't care about the sign of the data. But if you need signed or unsigned characters, you must be specific. Okay, now finally, I did not know. Why would you use a signed character B? I wonder why signed character B is used. Okay, now finally we can figure out the range of numbers if you assume that a character is 8 bits and your system uses the virtually universal 2's complement representation for signed and unsigned. if you assume that a character is 8 bits and your system uses usually universal 2's complement representation for signed and unsigned. Generally, if you have n bit 2's complement number, the signed range is minus 2 raised to n minus 1 to 2 raised to n minus 1 minus 1, and the signed range is 0 to 2 raised to n minus 1. So assuming those constraints, we can finally figure out ranges minus 128 to 127 and 0 to 255, and the ranges of character are implementation defined. Let me get this straight. Character is actually a number, so we can do math on it. Yep, just remember to keep things in the range of a character, a plus b. What about those constant characters in single quotes like b? How does that have a numerical value? The spec is also handy baby here, since C isn't designed to run on a single type of underlying system. But let's just assume for the moment that your character set is based on ASCII for at least the first 128 characters. In that case, the character constant will be converted to a character whose value is the same as the ASCII value of the character. That was a mouthful. Let's just have an example. Character A equals 10, character B equals B, that is ASCII value 66, and that is 76. This depends on your execution environment and the character set used. There's Morse code, Baudot code, Chinese telegraph, Murray code. I don't know. One of the most popular character sets today is Unicode, which is a superset of ASCII. So for your basic situation, you almost certainly get the ASCII values out of them. More integer types: short, long, long, long. So far, we've just generally been using 2 integer types, and we recently learned about the signed variants of the integer types. And we learned that character was secretly a small int in disguise. So we know the ints can come in multiple bit sizes. But there are a couple more integer types we should look at, and the minimum ranges they can hold. Your implementation probably has wider ranges than the spec requires, but the ranges here are the ones you can be certain are portally available. The header file limits.h defines macros that hold the ranges for various types. Rely on that to be sure and never hardcore assume these values. These additional types are short int, long int, and long long int. Commonly, when using these types, C developers leave the int part of long long, and the compiler is perfectly happy. Let's take a look at the integer data types and sizes in ascending order grouped by signness. Again, these minimum and maximum limits are what you are portably guaranteed by the spec. Your system probably has wider ranges. Minimum bytes 1, minimum value minus 28 or 0, 127 C, or 127 or 255. Why is this 100 over here? Yeah. So that was car. Signed car is minus 128 to 127. Short is minus 32768 to 26767. And we have int, we have long int, we have long int, we have unsigned character, unsigned short, unsigned int, unsigned long. There is no long type. You can't just keep adding longs to that. Don't be silly. 2's complements fans might have noticed something funny about those numbers. Why does, for example, the signed character stop at minus 127 instead of 128? Yeah, it does. Oh yeah, because it's 2 raised to n minus 1, right? It's the signed character stop at minus 128. Yeah, but in this it's not there. What do you mean? Remember, these are only the minimums required by the spec. Some number representations like. Wait, what do you mean the signed? Okay, weird. Let's run the same number table on my 64-bit 2's complement system and see what comes out. But we can see how my system has larger limits than the minimums in the specification. Yeah, it does. Minus 138, minus 138. Oh, why does, for example, the signed character stop at minus 127 even though it's not minus 127, it's 127? I don't know, man. Or am I tripping? I don't fucking know. So there is a little more sensible, but we can see how my system has larger limits than the minimums in the specification. What are the macros in limits.h? These guys. Notice there's a way hidden in there to determine if a system uses signed or unsigned characters. If character marks equals eukaryotic marks, it must be unsigned. Yeah, because Also notice there is no minimum macro for the unsigned variables. They're just 0. Makes sense. Double, long, double. I think the last challenge is to create, I don't know, should I create the program to display this type of what do you say, display this type of table? I guess I'll create that, right? nvm main.c hash include stdio.h and hash include limits.h. It's the limits.h, right? Oh my god. Void boomi. So printf type min bytes min value max value. Now it's the unsigned variance. What is the minimum value? I don't talk very much when I code. That is something I do. I don't talk very much when I code. No. Okay, what the hell happened? It does have /n and stuff, but it is not working. I don't want to use AI to figure it out. Okay, that's working. Wait, what if I do like this? Wait, is it all one? Oh my god, bro. There was something I no. Yeah, this is how I replaced, by the way. Was it percentage S? No, it was S percentage R. No. It was percentage S and do this, and it was /n and then do this and do /n. Yeah, what the fuck. Wait, I'm just gonna do it again. What the hell did I say? Yeah, slash and replace that with Boomi. What? Percentage S, boom, boom, no, boom, and do this, and boom, and boom. There you fucking go. There you go. Oh, there's one guy missing. Okay, who is it? Tell me, who is it? Who is it? Who is this guy? What is this guy doing here? Oh, why is my guy freezing? Signed character. Yeah. Wonder why this guy got fucked. Okay. What the hell? Why is it 127, 127? This is a bit spaced. Probably because the numbers here, yeah. So my long has -1 for some fucking reason. I don't know why. Right? Yeah. I don't know. Let's move on. More float, double and long double. How much is the charge? Okay, good. Let's see what the spec has to say about floating point numbers in The following parameters are used to define the model for each floating point type. Parameter definition. S sign plus or minus becomes 1. Plus or minus, right? B base or radix of exponent representation an integer greater than 1. E exponent an integer between a minimum E min and a maximum E max. P precision the number of base B digits in the significant. Fk non-negative integers less than Fb the significant digits. A floating point number x is defined by the following model. So x is the floating point number is equal to the sign times the base raised to an exponent, that is into the summation of k non-negative numbers less than b, okay, k to p, where precision is the number of thing, and fk is the non-negative integer less than b, where b is the base minus the k itself. Okay, cool. I hope that cleared the right up for you. Okay, fine. Let's step back a bit and see what's practical. Note, we refer to a bunch of macros in this section. They can be found in the header float.h. Floating point number are encoded in a specific sequence of bits. Is tremendously popular in bytes. Diving in a bit more, the number is basically represented as the significand, which is the number part, the significant digits themselves, also sometimes referred to as the mantissa, Yeah, that rings some more bell. And the exponent, which is what power to raise the digits to. What power to raise the digits to. Recall that a negative exponent can make a number smaller. Imagine we are using 10 as a number to raise by an exponent. We could represent the following numbers by using a significand of 1, 2, 3, 4, 5 and exponents of minus 3, 4 and 0 to encode the following floating point values. 1, 2, 3, 4, 5 into 10 raised to minus 3 equals 12.345, 10 raised to 4, and yeah. For all those numbers, the significance stays the same. The only difference is the exponent. On your machine, the base for the exponent is probably 2, not 10, since computers like binary. You can check it by printing the FLT radix micro. Okay, so main.c. printf. I don't know, I think it's the number. It's a number. FLT radix. Hashtag include declaration. What was it? Floats dot h. Was it floats or float? Float. Yeah, why would it be floats? That's dumb. 2. Nice. Now, so we have a number that's represented by a number of bytes encoded in some way. Because there are a limited number of bit patterns, a limited number of floating point numbers can be represented. But more particularly, only a certain number of significant decimal digits can be represented accurately. How can you get more? You can use larger data types. And we have a couple of them. We know about float already, but for more precision we have double, and even more precision we have long double, unrelated to long int except by name. The spec doesn't go into how many bytes of storage each type should take, but on my system we can see the relative size increases for 1816. So yeah, we can print that out using n main.c printf the size of, first we can do float, change in, oh my god, change in, boom, and double, change in, what was it, long double. We have 2, which was the float radix, and 4 is the float, and 8 is the double, and long double is 16. So each of the types on my system uses those additional bits for more precision. But how much precision are we talking here? How many decimal numbers can be represented by this value? Well, C provides us with a bunch of macros in float.h to help us figure that out. It gets a little wonky if you're using base 2 binary system for storing the numbers, which is virtually everyone on the planet, probably including you, but bear with me while we figure it out. How many decimal digits? The $1,000,000 question is, how many significant decimal digits can I store in a given floating point type so that I can get out the same decimal number when I print it? The number of decimal digits you can store in a floating point type and surely get the same number back out when you print it. It is given by these macros. So let's print those guys. Slash n. I'm just gonna separate them. So we have float digits, the maximum number of digits the decimal digits float can store, and we have double dig, and we have L double dig. 6, 15 and 18. Minimum is 6, 10, 10. Okay, nice. On my system, float dig is 6, so I can be sure that if I print out a 6-digit float, I'll get the same thing back. It could be more digits. What he's talking about same thing back is, if the floating point, if the float number per se is 15 digits, right, what happens when you get it back is it will truncate it to 6 digits. That's what he means by I'll get back the same digits. So I'll get the same thing back. It could be more digits. Some numbers will come back correctly with more digits, but 6 is definitely coming back. For example, printing out floats following this pattern of increasing digits, we apparently make it to 8 digits before something goes wrong. But after that, we are back to 7 correct digits. As you can see, 1 2 3 4 1 2 3 6 7 1 2 3 6 7 1 2 3 4 5 6 7 8 1 3 4 5 6 7 8 7 8 9, but it became 9 1, and then when, as you can see, it reached around 7 digits, and then boom, it gone. Let's do another demo. In this code, we'll have two floats that both hold numbers that are float dig significant decimal digits. The program numbers as it comments indicate on the system is one of 6 that uses okay, otherwise you might get different output. Then we add those together for what should be 12 significant digits, but that's more than we can store in a float and recover as a string. So we see when we print it out, things start going wrong out of the 7th digit. Both these numbers have 6 significant digits, so they can be stored accurately in a float. Yeah, because the 0 doesn't matter. These are the significant digits. Now if you add them, I guess I'm going to do this. nvm main.c, change in this guy, change in this guy, right? Float f equals 3.14159, that is the pi. Float g is equal to 0.0000265,358. So it depends on the number of significant digits that can be stored. Here 0 is not significant because without the 0 we can get the number back. Now we're going to add them up. 0.5f/n, and it prints f, right? Do this, and what the hell, print f, we have 0. I think 11 digits. That means, I think what the specific formatter means, the string formatter means is 0.5 means 5 digits. 5, the digits are on the left side of the point, decimal point, and 11 as well. So I think significant digits, I don't know what you call those things, but yeah, you get what I mean, right? Yeah, both of them are still correct. It has no fault. But if you add them, this is what happens. Printf 0.11 f/n f, and boom. Now if I do ccmain.c and do this, as you can see, this should have come I'm a bit too close. As you see, this should have come correctly. It should have come like a copy of this down here, but no, it became 2741001 because it cannot handle significant digits of more than 6. The above code has an f after the numeric constants. This indicates that the constant is type float as opposed to the default of double. More on this later. Oh, okay. Oh wait, no. This indicates that the constant is type float as opposed to default of double. So I believe the C language sees all these decimal points as double. Remember that FLT dig is the safe number of digits you can store in a float and retrieve correctly. Sometimes you might get 1 or 2 more out of it, but sometimes you'll only get FLT digits back. The sure thing, if you store any number of digits up to and including FLT dig in a float, you're sure to get them back correctly. So that's the story, FLT dig, the end, or is it? Converting to a decimal and back. But storing a base 10 number in a floating point number and getting it back is only half the story. Turns out floating point numbers can encode numbers that require more decimal places to print out completely. It's just that your big decimal number might not map to one of those numbers. That is, When you look at floating point numbers from one to the next, there's a gap. If you try to encode a decimal number in that gap, it will use the closest floating point number. That's why you can only encode FLT-dig for a float. I didn't get this. Can encode numbers that require more decimal places to print out completely. It's just that your big decimal number might not map to one of those numbers. That is, when you look at floating point numbers from one to the next, there's a gap. If you try to encode a decimal number in that gap, it will use the closest floating point number. Oh, so that's what it's trying to do. It has two numbers. It has two numbers, right, with its significant digits until reaching till 6, where 6 is the most safest bet for FLT-dig macro. But we are putting a number that is between those two gaps. What the compiler is doing is, or what at runtime what it's doing is, it's choosing a number that is closest to one of the boundary. That's why you can only encode FLT-dig forever. But what about those floating point numbers that aren't in the gap? How many places do you need to print those out accurately? Another way to phrase this question is, for any given floating point number, how many digits do I have to preserve if I want to convert that decimal number back into an identical floating point number? That is, how many digits do I have to print in base 10 to recover all the digits in base 2 in the original number? Sometimes it might be only a few, but to be sure, you will want to convert to a decimal with a certain safe number of decimal places. That number is encoded in the following macros. So, number of decimal digits encoded in a float, number of decimal digits encoded in double, number of decimal digits encoded in a same as the widest encoding. Let's say an example where dbl dig is 15, so that we only can have in a constant, but dbl decimal dig is 17, so we have to convert to 17 decimal numbers to preserve all the bits of the original double. Let's assign the 15 significant digit number to x, and let's assign this one significant digit number to y. Printed to 17 decimal places. Okay. But let's add them together. This should give us that, but that's more than dbl dig, so strange things might happen. Let's look at, okay, not quite right, should end in. That's what you get for printing more than nil, right? But check this out. That number above is exactly representable as it is. If we assign this number to z and print it, we get, it is exact, 7 digits correct, more than dbl dig. If we had truncated z down to 15 digits, it wouldn't have been the same number. That's why to preserve all bits of a double, we need dbl decimal dig and not just the lesser dbl dig. All that being said, it's clear that when we are messing with decimal numbers in general, it's not safe to print more than FLT-dig digits to be sensible in relation to the original base 10 numbers. But when converting from float to a decimal representation and back to float, definitely use a floating decimal dig to do that, so that all the bits are preserved exactly. I didn't understand any of that bit. I'm gonna reread this shit. Converting to decimal bank, but storing a base 10 number in a floating point number, that is the base 2, and getting it back out is only half the story. Turns out floating point numbers can encode numbers that require more decimal places to print out completely. It's just that your big decimal number might not map into one of those numbers. That is, when you look at floating point numbers from one to the next, there's a gap. If you try to encode a decimal number in that gap, it will use the closest floating point number. That's why you can only encode FLT-dig for a float. But what about those floating point numbers that aren't in the gap? How many places do you... Another way to phrase this question is, for any given floating point number, how many decimal digits do I have to preserve if I want to convert the decimal number back into an identical floating point number? That is, how many digits do I have to print in base 10 to recover all the digits in base 2 in the original number? Oh, sometimes it might only be a few, but to be sure, you will want to convert to decimal with a certain safe number of decimals. That number is encoded in the following macros, where dbl dig is 15. So that's all we can have in a constant. But dbl decimal dig is 17. So we have to convert to 17 decimal numbers to preserve all the bits of the original double. Let's assign the 15 significant digit number to x, and let's assign the 1 significant digit number to y. And if you add both of them, it will become 16. But let's add together. This would give us, but look at it, it doesn't give it because dbl digit is only around 15. That's what we get for printing more than db, right? But check this out, that number above is exactly represented as it is. If we assign 0.2 whatever it is 17 digits to z and print it, we get, oh, I think I get it now. 17 is correct, more than 17. If you truncate it now, it would have been the same number. That's why to preserve all the bits of a double, we need double decimal dig and not just the lesser. Oh, it's clear that when you, oh, okay, I understood. Oh, I understand it now. So what I understand from that is, please do correct me in the comments below. Change in do that's thing, that's now let's just say double x is equal to this number 0 0.12345623456 7 1 2 3 4 5 6 7 8 9, then what is that, 0 1 2 3 4 5 0 0, and I think that's 15. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17. That is not how much I need. Printed to 17. No 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 of them are there, or you could say 15 because these two are not that significant, right? Now double y is equal to 0 0.0000006 and 0. Now it's printed to 17 decimals, so I'm going to just do this. Yeah, right, but let's add them. Now print f x, and how do you represent double? How do you print double again in C? Floating point, octal number is there, is lf. Okay, that's weird. lf and x, right? Now print that shit, y as well. Now print f x plus y, lf x plus y. Oh, what the fuck? Oh, main dot c. How did I not see that? I don't like how it looks, so let's just do slash n. Oh no, slash n. As you can see, 0 1 2 3 4. Okay, I really need to do that. Point 17, point 17, and as you can see, what happened? Oh wow! Oh my god! Replace, yeah. As you can see, these are all printed in 17 digits, and it doesn't become 5 6, it becomes 5 9. That is not cool, right? Now the reason being that the digit is going outside, the DBL dig limit, right? But if I did something like double again, z is equal to x plus y, the funny thing is, it actually preserves the decimal digits when it comes towards decimal, right? It does preserve it, like it doesn't go away. Why is this point f z? Yeah, okay, cool. Okay, and if you do this and if I do this, it still preserves the number. So what do I mean by it preserves is, let's go that again. As you can see, you might think that it would have given a wrong answer, right? If you had truncated down to 15 digits, it would have been the same number. That's why to preserve all the bits of a double, we need DBL decimal digits. Yeah, it wouldn't have been the same number. More than, yeah. That's what we get for printing more than DBL digit, right? But check this out. That number above is exactly representable as it is if you truncate a z. Now, I do want to print f the macro for that. So what was the macro called? I think it was decimal DBL digit. Yeah, decimal, no, DBL decimal dig. In print sheet. Oh wait, did it did it get printed with the thing? Yeah, 17. Yeah, what I'm gonna do is I'm gonna add one more number to this. Four, five. This is gonna. So yeah, 0, 1, 2, and it didn't do the rest of the thing, but yeah. Wait, did it do the exact same thing? Yeah, it did do the exact same thing because it was trunk, but the 6 was not there. Yeah, it printed the same thing. Okay, I should not have done that. Look how many numbers I put. It truncated it to let me put 20, 20, 20. There you go. 1, 2, 3, 4, and 6. 6 plus 6 is not 12, obviously, right? 1, 2. These two will work. No, see, as you can see, it didn't work properly. The reason being that we went above 15 numbers, and yeah, this still holds. 1, 2, 3, 4, 5, 6. How many digits are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and it still preserved it. I guess it's still 19. I guess, yeah, it's not that far from it, right? I'm gonna do 7, 7, 8, 9 as well. Okay, and maybe 0, 1, 2, 3, 4 again. No, go back again, and let's just do 30 this time. It should break at some point. See, don't know. Boom. Yeah, this thing broke, which makes sense because this is above 15 decimal digits. This thing still hasn't broken down, I believe. This thing completely broke. This is not what the numbers should be. It still kinda has the thing, yeah. It still hasn't broken down, not gonna lie. That's cool. So it doesn't break down. All that being said, it's clear that when we're messing with decimal numbers in general, it's not safe to print more than FLT, dig, DBL, dig, or but when converting from float to a decimal representation and back to float, definitely use FLT decimal dig to do that so that all the bits are preserved exactly. Constant numeric types. When you write down a constant number like 1, 2, 3, 4, it has a type. But what type is it? Let's look at how C decides what type the constant is and how to force it to choose a specific type. In addition to good old decimal like grandma used to bake, C also supports constants of different bases. If you lead a number with 0x, it reads as a hex number. Hexadecimal case doesn't matter for hex digits. Nope. Booming. Booming. If you lead a number with 0, it's read as an octal number. So 0x is hexadecimal, 0 is octal, prints as an octal number. This is particularly problematic for beginner programmers who try to pad decimal numbers on the left with 0 to line things up nice and pretty, and admittedly changing the base of the number. What the fuck? Who would do that? People do that? No way, bro. What the fuck? 11110011. Maybe I'm not creative enough. 111100111011. Maybe I'm not that, not OCD. It's OCD is a a disorder. I don't want to make fun of disorders. There's already a lot of people misdiagnosing themselves or diagnosing themselves to get clout and shit. So I don't want to make that joke. Anyways, but I'm not that upkeep about numbers and stuff. Maybe that's why I can't. That's why I never thought about putting 0 as padding. You know what I mean? A note on binary. An unofficial extension. Oh, unofficial extension. It's lately surprised to me that C doesn't have this in the spec yet. In the C99 rationale document, they write a proposal to add binary constants was rejected due to the lack of precedent and insufficient utility, which seems kind of silly in light of some of the other features they kitchen synced in there. I'll bet one of the next release has it. Oh, okay. So like allows you to represent a binary with the 0b prefix. Yeah, 0b makes more sense. Prints 42 days. No, what? Yeah, 0b makes sense. There is no printf format specifier for printing a binary number. You have to do it a character at a time with bitwise operators. Integer constants. You can force a constant integer to be a certain type by appending a suffix to it that indicates the type. We'll do some assignments to demo, but most often devs leave off the suffixes unless needed to be precise. The compiler is pretty good at making sure the types are compatible. So that's long int, that's long integer, that's unsigned long and unsigned long. The suffix can be uppercase or lowercase, and the U and L or LL can appear either one first. Okay. None, no suffix, L, LL, U, UL, ULL. I mentioned in the table that no suffix means int, but it's actually more complex than that. So what happens when you have an unsuffixed number like this? What type is it? What C will generally do is choose the smallest type from int up that can hold the value, but specifically that depends on the number's base as well. The spec has a great table indicating which type gets used for what unsuffixed value. In fact, I'm just going to copy it wholesale right here. C11 6.4.4.1 5 reads, the type of an integer constant is the first of the corresponding list in which its value can be represented, and then goes on to show this table. So no suffix, so a decimal constant int or long int, so in that case int if it's a decimal. If it's an octal or hexadecimal constant, it will be first int. Otherwise it can be an unsigned int. If it's a u or u suffix, it will be an unsigned int for both of them. What's that saying is that, for example, if you specify a number like 1, 2, 3, 4 u, first C will see if it can be unsigned integer. If it doesn't fit there, it will try unsigned long int and then unsigned long int. It will use the smallest type that can hold the number. Oh, okay. So it will check, can this fit? No. Can this fit? No. Can this fit? Yeah. Suffix, that is for that. Oh, so what happens when you have an unfixed number? Like, what type is it? That depends. It chooses the thing. Okay, I wonder what. Yeah, long int. So it will do it on its own. That's what you're trying to say. No, it will do int or long int here, and it will do int unsigned. It can be unsigned int, long int, unsigned long int, long. Okay, okay, I get it now. If u was the suffix there, it will be unsigned int. If more, unsigned long int. Okay. The first C will check if it can be fit. It's u, right? Small u, big U. So it will check if unsigned it is a decimal number. So no, unsigned long int. Yes. Okay, does it fit there? It'll try it and then unsign out. Okay, floating point constants. You'd think that a floating point constant like 1.3 would have a default type of float, right? Surprise, turns out unsuffixed floating point numbers are type double. Happy belated birthday. You can force it to be type float by appending an F or capital F, its case insensitive. You can force it to be type long double by appending L or capital L. Sample, this whole time though, we've just been doing this, right? Is in the left a float and the right a double? Yes, but C is pretty good with automatic numeric conversion, so it's more common to have an unsuffixed floating point constant than not. More on that later. Scientific notation. Remember earlier when we talked about how a floating point number can be represented by a significant base and exponent? Well, there's a common way of writing such a number shown here, followed by its more recognizable equivalent, which is what you get when you actually run the math. Writing numbers in the form s into b raised to e is called significant notation. In C, these are written using the e notation, so these are equivalent. You could put a pun in there. Anyways. 1, 2, 3, 4, yeah, this. You can print a number in this notation with the %e format specifier. A couple little fun facts about %e. You don't have to write them with a single leading digit before the decimal point. Any number of numbers can go in front. However, when you print it, it will change the exponent, so there is only one digit in front of the decimal point. Okay, makes sense. The plus can be left off the exponent as its default, but this is uncommon in practice from what I've seen, because yeah, that doesn't make any sense. This doesn't make any sense. I mean, it does make sense. It's not very readable. Yeah, that's the word. It's not very readable. You can apply the F or L suffixes to e notation constants. Okay, hexadecimal floating point constants. But wait, there's more floating to be done. Turns out there are hexadecimal floating point constants as well. These work similar to decimal floating point numbers, but they begin with a 0x just like integer numbers. The catch is that you must specify an exponent, and this exponent produces a power of 2, that is 2 raised to x, and then you use a p instead of an e when writing the number. So 0x a.1p3 is 10.00625 times 2 raised to 3, which is 80.5. When using floating point hex constants, we can print hex scientific notation with %a. So hex scientific notation is %a, and decimal scientific notation is %e. That's the whole yards. Yeah. Type 3 is conversions, and I believe conversion is okay. There is a lot of conversions. What else is there in conversions? After conversions, no. Oh, qualifiers and specifiers. Oh, I'm gonna do the conversion and finish out conversion. So yeah, that's all it for types and more times. If you want this article, I'll be linking this article down in the description below. So anyways, bye guys.